Good afternoon from the East Coast here. This is Dennis Keene from XCD Environmental. We'll be starting in a few minutes as people start to pile in. Just please wait a moment, we'll get going. Thank you. It's about 1 o'clock now. I'm just going to give folks another minute to finish logging in, and we'll get started. Thank you. Okay, we're going to get going here. First of all, I'd like to thank everyone for showing up on this Wednesday for the XTD Environmental webinar on in situ chemical oxidation. Just a couple of initial webinar fun facts. I should note that fun facts are rarely fun, and these items here are no exception. All participants will be on mute during the presentation. Approximately about 1 day after this webinar has been finished, we'll send an email to everyone, and that will allow you to download a copy of the webinar. We're also recording this webinar, so we'll make that available also likely in that same email. And then on the panel that you have, I believe on wherever you happen to dock it, there's a questions section where you can ask questions for either myself or Scott Crawford. Questions will be answered at the end of the webinar. If we miss questions, we have a lot of material to cover, so we may run a little short on time. If we don't have a chance to answer them, then what we'll do is we'll follow up via email after the webinar and as soon as we can. So what we're presenting here is state-of-the-art versus state-of-the practice for in situ chemical oxidation. We work for XCD Environmental. XCD Environmental is a remediation firm. We do in situ and ex situ remediation for groundwater and soil. Originally started about in 1997 by Mike Marley and Ed Drosty. My name is Dennis Keene. I'm a PG. I've been working for XCD since 2000, so I have about 20 years in the business. Scott Crawford, who will be presenting after me, he is a professional engineer. He has been in the business for approximately 25 years. I tend to concentrate a bit more on the science side of things, geology being hydrogeology and modeling and that kind of information. Scott tends to do a bit more of the engineering. So what should you come away from this webinar with? So basic understanding of the state-of-the-art, right, implementation process for ISCO applications. We like to emphasize basically understanding as much as we possibly can prior to implementation, and then using that information as much as possible to get the highest success rates that we can for our applications. The big thing we'd like to focus on is the pre-design activities. Those are often minimized, but the question really is at what expense? How much does your uncertainty increase based upon minimizing those pre-design activities? I'll be going over those first two bullets during the presentation. Scott Crawford will pick up on the pilot tests. So he's going to go over pilot tests, what are the useful and what are the different configurations that you can use in order to figure out the additional design parameters you need for your full-scale application. And then finally, the full-scale applications, what are the different configurations? What are the common pitfalls that we have for those? So We are going to go through a lot of conceptual understanding of in situ chemical oxidation. We're not going to get too much into the technical details of the chemistry and so forth, but we do have at the end of this presentation some additional slides tacked on that go into quite a bit of the chemistry and technical information. So while we're not going to review it during this webinar, we are going to have it available for you when we actually go out and do the when we do the email in a day from now. So pre-design considerations. This Charlie Batch is an NFL player, a quarterback, and then also a broadcaster for a while. And he basically said proper preparation prevents poor performance. And we believe in that, especially for in situ chemical oxidation design. We have a couple of images here. On the left-hand side, we have, for chemical oxidation, a couple of things that you really need for it to be successful is contact is the big one, and dosing, right? Having enough oxidant in order to basically meet your objectives. Set up on the left-hand side here, contact and dosing is likely to be a lot more successful than the poor SAP on the right here. Clearly contact with that water bucket is hitting more of the wall than it is to the room that needs it. And clearly the dosing requirements, the amount of water that poor person can deliver is minimal relative to what they need for that particular situation. So we like to make sure that we abide by these type of concepts when we actually go to do our design as applications. So cost-effective solutions, and then this slide is meant to describe what is that. Excuse me for a second here. What does that mean, right? What is a cost-effective solution? So there are new products being brought into the market relative to chemical oxidation, right, that we can apply to our environmental sites to try and achieve our objectives. Often marketed as simple, better, more cost-effective. But we still feel that you need to understand some of the basic concepts of those products so that you can avoid failures, right? What's the practical limitations of those products? How do they work? More importantly, what type of failure mechanisms are they more likely susceptible to? And then what is the cost of having an application that doesn't go or meet objectives, right? What's the cost of a do-over in that standpoint? So these are some of the concepts we'd like to think about prior to going into an application. So really we want to make sure that we're putting the effective into the cost effective, right? We don't believe that cheap is necessarily cost effective in this particular instance. And part of that process is the pre-design engineering impact, right? We like to make sure we understand as much as possible going into an application prior to doing the application. So initially, what do we want to understand? We want a solid conceptual model, right? What is the contaminant type? Certain oxidants don't work on certain contaminants. What is the phase? We talked about NAPLs, dissolved, sorbed phases. Where's the location of it? Is it in a high permeability material, in a low permeability material, right? Is it susceptible to advective injections, or is it more diffusion based? What's the properties of the media can be very important, right? Is it high organics, that kind of information. Oxidant selection will depend upon many of these things, what our dosage is, and then step 4 is pilot testing. And I think that the big thing here is to understand is that setting expectations is really, really important. Prior to going through the oxidant selection and many of these pre-design activities, there'll be maybe a certain expectation as far as how that might perform. And then once you get through all this, it really is a good idea to circle back and understand, okay, what are our expectations for this? Is it going to meet where we thought it's going to meet? If it isn't, is it worth to keep going down this path? Or if it is worth it to go down this path, do we have to temper expectations possibly? And it's a really important aspect. So step 1, conceptual model. So we're going to go to a little more detail here. So contaminant properties. What's the effectiveness of the oxidant chemistries, especially on a particular contaminant, right? So a permanganate does not work on benzene, right? So the question is do we have benzene in the subsurface as a contaminant? Will that limit to the type of oxidant chemistries you use? Is there preferential oxidation of certain contaminants, right? Are you going to basically chew through a particular compound before the other ones, and which ones are more important from your project goals? Mass of contaminant, really important, right? The amount of oxidant that you add to the surface can be proportional to the mass of contaminant and also the natural organic demand of the soils, right? So if you have a large mass of contaminant, let's say it doubles, right? That can potentially double the oxidant that you need to use and impact things like cost and application time and aspects like that. What phase is the contamination in? So aqueous phase. So if we're doing an injection in our contaminant, like let's say a 1,4-dioxane is mostly in the aqueous phase, when we do that injection, are we really gonna be able to make contact with it, or are we just going to push it around? Sorbed, right? Is it sorbed to the soils when we do an injection? It's clearly gonna stay likely in place. We're not gonna push it around as much, but then also we might have to treat the soils too on top of that. And as mentioned earlier, NAPL, right? Is it an L-NAPL? Is it D-NAPL? Is it stringers with a very high surface area to volume ratio, or is it pooled, right? ISCO generally happens in the aqueous phase. If we have pooled D-NAPLs, then you're not necessarily going to get the contact you need with a pooled NAPL. So it's another question. Where's the location, right? So are we talking about something that's above the groundwater table, below the groundwater table? Is in the smear zone? Are there structures nearby? Are there sensitive receptors? These are all the kind of things that we need to worry about. And then media properties, permeability, I mentioned that earlier, right? Low or high permeability affects your ability to make contact and whether something's diffusion limited. Your oxidant demand, right? If high organic compound or high organics in the soils or a high oxidant demand, that can directly affect chemical costs, and that can basically impact whether or not the application is going to be feasible or not. And then impact on oxidant stability, right? We want to understand a bit about how long is the oxidant going to persist in the subsurface relative to something being diffusion limited, right? Or if you have very high groundwater velocities, right? Are you going to flush your oxidant after the injection outside of the area that you're looking to have it stay in? So these are all very, very important things to understand. Oxidant selection. So again, step one kind of feeds into step two here. So nearby structures, or is this an active facility? Are they habited? Are there people in it working? Off-gassing, right? If that's an issue, right? Hydrogen peroxide. Generally, for every gallon of hydrogen peroxide you inject, you can generate about 10 gallons of off-gas. So is that going to be a problem for your site? Lower permeability materials, right? So we need longer residence time for the required oxidant, right? Those lower permeability materials, essentially, you're not going to be able to inject the oxidant into them very much. So essentially, you can have very tight spacing as far as your injection wells go, or you may need to inject into a more permeable zone and have it diffuse out. Chlorinated ethanes, right? Higher energy oxidants are needed for those, like an activated persulfate, right? So that contaminant type only works with certain oxidants. And then are the impacts part in the vadose zone, right? So at that point, are we looking at something like an ozone, which is a gaseous oxidant, or are we looking at mixing, right, in order to have the oxidant contact the contaminant? And then we talked about D-NAPL, it may be a two-step process at that point. We're looking at maybe excavation, thermal, or some other type of technology, and then you could follow that by ISCO polishing, which might be the cheaper version of just doing entirely the other two or the other three items. And again, the contaminant type limits our oxidant selection. So I'm going to go through a little case study here, and this is actually for oxygen release type compounds, but it's analogous, very analogous to a standard chemical oxidation type process here. So again, we talked a little bit about pre-design engineering and understanding kind of where your failure mechanisms are ahead of time, and understanding what kind of dosing you need for your full-scale application, right? So, and I want to state up front really quickly here is that there's a number of vendors that supply compounds that release oxygen, and those products are excellent. We use them regularly in our applications, and they work really, really well. What we're more concerned about is making sure that we understand the quantity of reagents we might need in order to do an application. And so what most vendors will do is for a initial estimate, right, they will get you kind of a minimum dosing requirement based upon spreadsheets that they have in-house. But the issue with those spreadsheets, and many of the vendors will tell you this, is that a lot of the variables associated with those spreadsheets have a very high variability, sometimes orders of magnitude, right? TOD can give you anywhere from 1 to 100 grams per kilogram. And there's other interferences and scavengers. So those spreadsheets really can't account for those very site-specific items unless you already measured for them. So there's an issue there. The vendors will often tell you look, this is our initial estimate. What we recommend is for you to go out and actually do some testing to better define your actual dosing parameters. But in the sake of cost, a lot of times that can be ignored. So, and we think that's a mistake generally. So this is the case study I was talking about, and this is a Superfund site and had multiple source plumes with some chlorinated solvents associated with them. And what we had done is the idea was to look at different oxygen release products for a petroleum plume and try to understand if which one was more cost effective relative to their percent oxygen they contained, and figure out what the dosing requirements were. So what we did is we went to 3 vendors and basically got products from them, and then also used asked requests for their maximum dosage requirements for the oxygen release compound, right? So we had tested those 3 products at their highest recommended dosage, right, based upon their initial estimates, right? And again, the vendors basically noted that they recommended treatability testing to validate dosage assumptions, but we did the testing just as if, that's the only information we had was their recommended amounts. So here's the graph. So this is for the oxygen release compounds, right? And each one of these, I want to note here, is a dose, right? So essentially dose 1, right? Percent contamination reduction on the left here, and the dosage on the bottom here on the x-axis. And for each one of these, essentially, if the spreadsheet was 100% correct, we would have had 100% contaminant reduction. We would have hit we want to grade to the 90% reduction in a single dose is what we're looking for, right? So dose 1, right, the maximum reduction we had was about 18%. Dose 2 was 45%, and the maximum reduction we had for dose 3 was 57%. So as you can see, as opposed to having just a single dose meet that 90% reduction, right, we had done 3 doses, and we only reached 57%, right? So clearly, the site materials that we had used in the bench, right, were different enough, right? Their variability or their demand for oxygen in those soils were much higher than what was initially assumed in the vendor spreadsheets. So bench testing, why do we do these bench testing? So as we saw previously in that example, it can really be important relative to meeting your objectives. The big thing is for in-situ chemical oxidation is calculate your total oxidant demand, right? This can vary by orders of magnitude, as I mentioned, has a significant impact on effectiveness and cost. We use this to determine the ability and kinetics of the oxidant. So we'll make sure that we can get the compounds that we're targeting down to the criteria or the goals for the sites, and that they'll get them down to those levels in the time frame that we want. You can determine catalyst activator requirements if you need to. You can evaluate byproduct information, metals mobilization, and then there's additional observations in there also. It's always with the eye towards full-scale implementation. As I had mentioned, the soil demand can be anywhere from 1 gram per kilogram to 100 grams per kilogram. We recently had a bench test that was done in-house that had about 250 grams per kilogram, and as you can imagine, the office was all a Twitter about it. It was a pretty high value. So at that particular instance, we were able to direct the client towards an alternate technology, because at 250 grams per kilogram, the amount of oxygen that was required for that application would have been very large and cost prohibitive at that point. So factors that affect the total oxidant demand, right? So this is the total amount of oxygen that were required to satisfy both, the organic matter, reduced metals, minerals, the mass and contaminant, right? And we really want to understand all of those things. Additionally, for a number of oxidants, the applied oxidant concentration can affect the oxidant demand. So if you test something at 100 grams per liter as far as the injection concentration, right, but you apply 250 grams per liter or 200 grams per liter, your total oxidant demand can change. So it's really important to try and mimic the injection concentration that you're going to be doing in the field. The big thing here is some bench studies can give false positives, right? So the big thing that we try and do is simulate subsurface conditions. If you're not simulating subsurface conditions, then you may have an issue when you go to the full scale. If you use non-representative TOD, total oxidant demand, or contaminant mass, again, a lot of these are done on soils. When we do them on soils, it's very hard to get a sample that's representative of everything that's at the site. So that can be an issue. And then the oxidant behavior is not taken into account. Next, we have an example. So this is an example of a bench test that we had done peer review on. This was a catalyzed hydrogen peroxide bench, and it was considered a success. It had basically reached non-detect in the reactor for TCE. So, it was considered that, the catalyzed hydrogen peroxide, which was 4, would be an excellent oxidant to use in the field. We were brought in to do some peer review, and from the actual information gained by the clients, we noticed that the half-life is only 5 hours, right? So if you're trying to inject over a 16-hour time frame, let's say, you're going to have a difficult time getting out to your full radius of influence. The other issue was gas generation. There was a lot of gas generation which was not reported. So when you do that amount of gas generation, essentially, you're not necessarily getting your hydrogen peroxide all the way out to your full radius of influence, and it can also result in stripping. If you look at the amount of loss of TCE and the treatability, the question was, well, how did they get ND in the test reactor if the half-life was so low? And the real question here is, or the answer to that is the TC vapor concentration measured in the off gas. So they took a sample in the off gas, and what we had done was looked at the theoretical volume of gas generated from the dissociation of the hydrogen peroxide. And when you use that versus the TC vapor concentration, you realize that the vast majority of the TC was actually just stripped. So it wasn't destroyed, it was just actually transferred to a different phase. The other thing about this particular case study was 21 pore volumes of reagent solution was used, right? So this is a common state of the practice issue. We tend to like to use 1 to 2 pore volumes in our treatability studies. They did the full scale based upon this bench test, this treatability study, and they injected about 12,000 gallons of CHP. They had a lot of off-gassing and daylighting associated with just due to the short half-life and the dissociation of the hydrogen peroxide into oxygen. Concentration of TC in the source area actually doubled at this point, so they generally probably just degraded a bunch of organic matter and didn't actually were able to degrade much of the TC. If you use the actual degradation ratios of the treatability relative to the amount of oxidant they applied in the field, they are likely only stored or only destroyed about 4 kilograms of TC was removed. So for this particular case study, they had the wrong oxidant, right? The hydrogen peroxide was dissociating too quickly and really just causing phase transfers for the TC. The wrong dosing, right? And an understanding of how to properly perform the treatability study would have helped them avoid this failure in the field. And so here's an example, and we'll see if we can get these to play here. This is alkaline activated sulfate, which generally doesn't. I'm going to hit pause here. Excuse me. So there we go. So the activated alkaline persulfate generally does not generate a lot of gas in the field, right? But in this particular bench test on the left-hand side here, there was a high organic matter in the site material, so it tended to generate a lot of gas. So one of the things you can avoid by looking at this information at the treatability scale is you avoid kind of the gas generation that you might see on the right-hand side here, which is associated with this field event. And that's it. I'm gonna pass this over on to Scott Crawford here, who's gonna go through the pilot study design in full scale, and then we will go from there. So Scott, if you just hold on a second here, I'll give you control. And we should be good to go.
Okay, Dennis, can you hear me?
I can hear you. Please go ahead.
Okay, thank you. Okay, so thanks, Dennis. That was a good review of some of the treatability design aspects. A lot of that is focused, as Dennis said, on the chemical design of a system, and we find in practice that a lot of people do focus on that initial chemical design, choosing the right oxidant for your contaminant, which is absolutely a critical step. And there's a lot of different products, a lot of different types of oxidant technologies that are out there that all work, and they have their place for sure. But where we see the next step in this overall state-of-the-art of the design. And when we call it state-of-the-art, one of the things I like to say is it's actually not really state-of-the-art. This is actually the way things should be probably done, is that you go through your design steps, one step at a time. But what we found over the years is because the technology has matured, people tend to feel like, well, these are known technologies. You don't really need to do as much design and engineering up front anymore because they're well known. But it's actually not the case, because every site is different and there's a lot of chemical challenges. But when you get to a pilot phase, you're actually looking at more of the physical aspects of your design that you're actually testing. Let me just see here. Okay, good. So the big difference between when you're scaling from a treatability study into the real world in a pilot test is there's a big difference between what happens in a treatability test in the test tube. You have ideal contact between your oxidant and your soil and your contaminant. So things are going to work a little bit better, obviously, in the treatability. Your pilot test is really designed to look at more of the physical contact, the distribution aspects of your process. And so you want to be able to make sure that your design is going to work in full scale. And you can get some of the simple or the standard information from your pilot test, like what kinds of flow rates are you going to be able to achieve, what kinds of injection pressures do you need. And that's important for when you're doing your design and you're trying to figure out how long a full-scale application might take, just based on injection rates, and that'll help you establish cost. But there's a lot more to it, and there's a lot more data that you can get from these pilot tests that are important to making sure that it's a successful application. And so, in general, why pilot test? Should you skip it? Why not just go to full scale? You can, but it's very risky. And by doing your pilot test, it is a cost. They're not cheap to do a good pilot test, but it does reduce the overall risk, and it can increase the certainty of your application. And in worst case, maybe it doesn't increase the certainty, but it allows you to manage your expectations, because there's only so much you can do if you find that the conditions at a site are not going to allow you to get to your contaminant reduction goal without immense effort. It's good to know that up front. Okay, so what kind of data do we want to achieve in our pilot test? So these, the items on the left, they're all pretty obvious. Radius of influence, flow rate and pressure. Those are the types of things you want to get from your pilot test when you're doing your field injection. And some of the things like flow rate and pressure is important, but it's actually much more complicated than this, because when you're injecting an oxidant, if the oxidant has a very short half-life or it's unstable, you want to make sure that you're injecting fast enough in the field so that you can distribute that oxidant and it actually makes it out to an appreciable distance from your injection point, so that it actually achieves the reactions that you want. If the oxidant is reacting too quickly when you're injecting it, it may only migrate out from your well screen a few feet, and then it's basically utilized and gone. And it doesn't, even though you're pushing the solution or the residual out further from your injection point, it's no longer effective. So understanding what your flow rates and your pressures are in your pilot is very important, because it can tell you if your if you have to change your oxidant or stabilize it further, or if it just won't work because the soils might be too reactive. There's a number of other things, but you really need in your pilot test is a robust monitoring plan. It's looking for the other groundwater parameters while you're injecting, looking at pH, looking at ORP, looking at conductivity, some of the standard parameters that we usually monitor during any groundwater sampling event. All of that's very important during your ISCO event, because those are the things that will help you to determine whether or not your oxidant is migrating where you think it is. And sometimes you can't rely on just your oxidant concentration as your tracer, if you will, because the oxidant can be reacting more quickly. So you have to look at these other parameters, these non-direct parameters like pH changes, conductivity changes, etc. And that's where the monitoring comes in, and being able to interpret those different lines of evidence to help you to establish that you know where your oxidant went and you know what your radius of influence is. Okay, so some of the traditional pilot test design layouts, and we've all seen these before, I'm sure, the standard direct injection test through either fixed injection wells or through direct push. You've got a central injection well with a number of multi-level piezometers spaced at different radii from your injection point, possibly at different directions to look for an isotropic distribution of the oxidant. And some of the keys here, this is your standard test. A lot of times we don't see even this level of a pilot test network because it costs a little bit of money, obviously, to put in a number of wells, and they're tightly spaced. People want to avoid that cost if they can. But it's so critical to get this type of layout if you can, and if the site's amenable to it, because it really does give you a lot of information on how well your oxidant is going to distribute during your full scale. And careful selection of your well screens and where they're placed in the geological, I don't know if people can see my mouse, but assuming you've got a stratified situation within the geology, you've got a target layer that you have your injection well screened into, and you have very discreetly screened piezometers in your target interval. You may need to put other multi-level screens in zones where you either are hoping that some oxidant gets into maybe this upper zone, or maybe you don't want your oxidant going into that zone, so you have additional well screens placed in areas where you're hoping your oxidant doesn't go to. But careful planning of your layout and having enough discrete monitoring points to really focus in on where exactly that oxidant is going is so critical. A lot of times we see people, when you have a number of monitoring wells that are already available at the site, you're tempted to use them because they're already there. They're technically free at this point, but they may have very long well screens. And when you have long well screens that are spanning multiple geological zones, you don't always get a clear picture of where your oxidant's going. So if you can put in dedicated and discretely screened monitoring points, it is very beneficial to the overall design and then to interpretation later on. Okay, so that's a standard layout that we typically would do or recommend or see other people do. Sometimes either the geology or where the contamination is located, it may be located in a very stratified zone, or it may be in, like, say, weathered bedrock or something, or fractured bedrock. And sometimes a test called a push-pull or a pull-push test can be possible for that type of orientation. If I can get the little animation to go here. It's not working. Oh, well. Just envision that you're basically injecting solution into those monitoring, those injection points, and then you would, once it's reacted in the ground for a short duration, you would then extract the solution. And then when you're extracting the solution, you can monitor what the concentration of the oxidant is. Maybe you have a tracer that you've added as well. And you can get an idea as the concentration that you're measuring in the extracted fluid as it changes. You can get an idea of what potentially the diffusion of the oxidant was into bedrock porosity, or you can also look at it's a measure of the oxidant demand that's been occurring in the subsurface while you've done that test. It's not going to work. This is what happens sometimes in the field. It actually doesn't. You have equipment problems, but we're not getting our animation. So, the establishing contact, and this goes back a little bit into what Dennis was talking about, is understanding your contaminant properties. So when you're designing your pilot test, you may find that you've got a contaminant that, like TCE, and this table showing that a lot of the TCE will absorb to the soil, and there's some mass of TCE in the groundwater, and but the majority of the TCE mass should be on the soil. But things like vinyl chloride, and this is just simple theoretical partitioning calculations, they, that contaminant, it's generally less absorbed on soil, and it's more of the mass tends to be in the dissolve phase. So when you have a situation like this, one of the concerns over the years is if you have a highly dissolved contaminant, you may need recirculation, or you have to be careful about how you're injecting, because you don't want to displace the source or disperse that mass that's in the groundwater. Although I'll say that in general, we don't typically see a lot of migration during these injections, and it's simply because even though the vinyl chloride in this example, it's likely associated with the dissolve phase, a lot of where the vinyl chloride is located, it's not mobile. It's in the immobile porosity of the soil. So it's not really, you may move and migrate some of that vinyl chloride, but you're not really going to displace the entire plume during an injection. So, I mean, if that was the case, then pump and treat would work a lot better, right? So you still want to be aware of it if you have sensitive receptors that are nearby, and you don't want some of these more mobile contaminants to be moved. So here's some the recirculation methods, and maybe this animation will work. I guess it will probably not. I was hoping it would work because it looked really cool. I can just assure you all that that was really nice animation right there. But the closed loop recirculation is a way where you can deal with the potential aqueous displacement of a plume. You can limit that. You can also use these types of methods to transport oxidant under an obstruction, maybe under the edge of a building, or completely under a building or an area that you can't access. But in general, recirculation also can help a lot with just general distribution. It shouldn't just be considered for special situations where you have to get under an obstruction. It can actually improve the distribution quite a bit. It's just, it is more complex. You've got more equipment, and you have to consider that as a cost item and if it's beneficial. But there are a lot of advantages to doing recirculation. So one way, again, these animations are not working, but okay, I guess they're not going to work. So the recirculation, if you need longer contact time, one thing this was going to show was one way to get, say if you have, I don't know if hopefully people can see the mouse, but if you have contamination that's penetrated into these silt layers below your injection points, and you've got a permeable zone where you can inject, and in your design phase you realize, I really can't inject directly into the silt zone. I've got contamination that's diffused into the silt zone. What I can do is I can rely on diffusion transport of the oxidant into these silt zones, and you can get a little ways into the silt and get direct contact, but it takes a while for that to occur. So you can basically either just inject a number of doses, and every time you dose, you're allowing diffusion to occur, and you're affecting the contaminant source in the silt zone. And there's limitations to this. There's only so much, and this is how you can manage your expectations for full scale. There's only so much oxidant that will get into these silt zones over time and practically, and that's going to be something that factors into your full scale planning and decisions on the next step. So that if you're doing this with multiple doses, just straight injection doses, you can do that, or you can do a recirculation process, and again, the animation's not showing, but if we were recirculating a constant concentration of oxidant between these two wells and replenishing the oxidant above ground, then we would maintain a high concentration of oxidant in contact with this interface between the sand and the silt, and then that would make a maximum concentration gradient, which would help to accelerate, or accelerate's probably not a great word when you're talking about diffusion because it's still going to be slow, but it's going to enhance the diffusion into the silt zone by maintaining that high concentration. So that may be another reason why your pilot test may incorporate a recirculation process. So just as a quick summary of some of the design aspects, and we just touched on some of the main ones. There's a lot of physical parameters that you're going to want to establish and determine during your pilot test. You're going to need a pretty robust monitoring plan to really assess that radius of influence and to make sure you understand what the contact is between your oxidant and your soil and your contaminant, because that's really the most important part of ISCO applications. So we want to get physical with it. That's what the pilot test is for, and make sure that we are answering the critical questions. And again, these questions are somewhat, they seem obvious when they're written down like this, but it's amazing how often some of these basic questions are not asked. Like, am I just simply putting in enough oxidant to react with the mass of contaminant that's present? Can I actually physically put the volume of oxidant into the ground and then deliver that oxidant mass? And if you have tight soils or you have highly stratified soil, you might not be able to physically do it, and your pilot test can tell you this. Am I going to have other issues? Sometimes you end up with, you feel like you have a perfect site that might be all sand, easy to inject into, but what happens is you inject your oxidant and then you go and you look for it and it disappears on you, and you wonder, hey, this was easy. I thought this was a piece of cake site, but the groundwater velocity was fairly high in that example, and it may have flushed your oxidant out of your target zone more quickly than it could react. Or we've seen at some sites like that where you have density-driven transport affecting that distribution. These oxidant solutions are denser than water, so they can sink, and in some cases they can sink pretty rapidly. And if you are not accounting for that in the well placement and where you're injecting, you can have that surprise when the oxidant isn't where you think it is, even in an ideal condition. So even under ideal conditions, it is important to do those pilot tests. Okay, so then this is now scaling from pilot to field, and this just little photo here is one of the larger types of systems here. This is a potassium permanganate automatic or semi-automatic batching plant for a fairly large-scale injection system. So they can be quite complex, and so it's obvious when you have a potential system design that's going to look something like this, that doing a treatability and doing a pilot test, it all makes sense because you're talking about major infrastructure that's based on those pre-design steps. But it still makes a lot of sense on the smaller sites to also go through the treatability, go to the pilot, because the exact same issues that affect the success of a large site with this kind of equipment, they're exactly the same for the small site. So it's equally important if you want to get the results that you're hoping to get.
And Scott, this is Dennis here. Sorry to interrupt you. We can see your mouse, just so you know. So we can see you moving the mouse around when you're pointing.
Okay, good. Thank you.
No problem.
So the overall considerations for a successful full scale, and Dennis already reviewed these, it's critical to get a good characterization of where your contamination is and understanding exactly where the majority of the contaminant mass is. A lot of times, if we don't have the information during the standard remedial investigation, just doing even a single boring with a detailed vertical delineation to show that where that mass is on a vertical basis is so helpful in design designing and targeting your contaminant mass, because ISCO chemicals, they're non-selective. So you really want to put your oxidant where your mass is. I guess that sounds like put your oxidant where your mouth is, but put your oxidant where your mass is. So getting that distribution dialed in tightly is very important. And there's a lot of good tools today, MIP tools and others that are very, you can do rapid assessment and get a much clearer idea of where your contaminant is. And if you can surgically target, you're going to have an increased success. And again, that's a cost, but it's so important to getting the result that you want. Adequate oxidant loading, we've already talked about. Treatability testing kind of answers that question. Establishing contact is where your pilot testing comes in, and making sure that it actually performs and you can get the injection parameters that you need to get suitable treatment. So those are your steps. And then when you get to full scale, you really still need to be monitoring and doing real-time field adjustments during these applications. The pilot testing is looking at one area only, or maybe a larger pilot test might cover a little larger area, but you're still moving and expanding your design to be over a larger area. So you may require some additional adjustments. So continuing that monitoring, making sure that the soils are similar throughout your area, and maybe you have to adjust your activator loading, your pH buffering, or something has to be adjusted to make sure the process goes smoothly. So it doesn't end with just the design phase. Some of these concepts do go into the field full scale. So I'm going to move through. So the full scale injection strategies, we've already sort of touched on some of these during the pilot. The direct injection, strategies are what typically is going on. Advective transport, that's where you may do a direct injection, but you're allowing the oxidant then to move with groundwater under an obstruction or under a road or something. Usually you have less contact, doing those types of strategies. So if you can avoid it and get direct injection, then that is always better. Recirculation is going to be an enhanced way to get better distribution, et cetera. So I'll talk a little bit in the next slides about some of the other high pressure and specialized tools that are available. And one thing we don't really talk about in this webinar is solid oxidants. That's definitely something to consider. There's products like potassium persulfate that Petroleum makes. That is a slow release oxidant that can be emplaced through fracturing or mixing, and those have their applications, but we won't necessarily talk about those in detail this time. So if I had the ability to see everybody's hands and ask the question, what do people think the number one failure mechanism is for a full-scale application? I know everybody would guess, let's see, low injection volume. And I wonder, I would like to have seen a poll on this to see if everybody agreed with that, because that's what we see, though. We see that most times when we're looking at where an oxidant application full scale didn't go according to plan, it's usually because there was a very, very low injection volume. And so simply just putting in enough pore volume of liquid can make a huge difference in the application. So simple enough, it just doesn't get done because it's more costly to have a large injection volume, more time, more equipment to do those types of applications. But it really can make or break an application. So the next issue that we tend to see is you'd think it's maybe the chemistry, but it's actually not the chemistry. It's back to contact. I would have suspected that most people probably would have guessed, which would have been a good guess, that limited contact between the oxidant and the soil is the number one reason. But I guess that is sort of interrelated with the injection volume being too small. But when we're talking about limited contact, we're talking about not only the physical contact, but also contact over time is critical. And when you have, say, a layer of contamination that's absorbed into, say, a silt clay unit or penetrating into a weathered bedrock that you can't directly inject into, that time of contact and the ability for the oxidant to penetrate into these zones through diffusion or through other mechanisms, that's critical in the design. And that's where understanding where the contaminant is so critical. If you know that it's focused at those interfaces, you can really design carefully and allow for that contact time, and you can get the best result. But, you know, of course, there's still limitations. There's only so much you can do in those situations, but you can optimize as best you can by using some of those strategies like recirculation and just careful planning of where the oxidant's going to be and how long it's going to take to penetrate into those zones. Oxidant stability, a lot of this can be determined at the bench scale, but sometimes it can change in the field. This little site diagram, it's kind of hard to see, but there's a transition zone where there was the soil was similar, but the soil was actually through biological activity that had gone on. There was a lot of metals and other reduced species here that were they were actually behaved much differently than the upper silty sands. So the whole design was based on the upper silty sand, but when you actually got into this previously unknown transition zone, there was a different geochemistry in that layer, and that would affect your performance in the field. So having that good conceptual site model is really critical. And also in this case, there was a high groundwater velocity in the area, and it was flushing the oxidant out. So getting that a highly stable oxidant is usually a good idea, but if it's too stable and it reacts too slowly, it actually can work against you if the oxidant is wasted effectively if it gets flushed out of your area. So you kind of want to be in that Goldilocks zone and make sure that you're not too stable and it's not reacting in the zone that you want. And then there's everything else that can go wrong, which that could be a whole webinar in and of itself. So the injection tools for more difficult conditions. So we were talking more about direct injection into sandier, less silty material where fluid flow can occur. When you get into these silts and clays, it's very difficult to directly inject into those, but there are a couple of tools that can help along those regards. So you have pressure pulse technology. This is something we've used a couple of times. It's still for fairly permeable soils, but it creates a pulse where the soil pores dilate slightly, and it helps to enhance the flow of the solutions through the tighter soils, or even in normal soil, or permeable soil, it can help. There's a couple of people who deliver those types of technologies. There's fracturing technologies. Those are for the slurries or solid oxidants that can be injected. Water jet, this is maybe a little newer variation of the fracturing, where a water jet at very high pressure can be used to cut a notch into the soil at your depth that you want to create a controlled fracture, and then you fracture at that interval, and those are a little better control. But all of these technologies, they're all still governed to a certain extent by preferential pathways, existing fractures, and things don't always go where you expect them to go. So there's always going to be limitations, but these tools can help to potentially improve your ability to get oxidant to where you need it to be. And then modeling. We didn't talk about it, but anything with state-of-the-art in it has to include modeling. So, but this is something that should be considered up front. This was a site where the blue area is the overall contaminated source, but the majority of the contaminant mass was delineated to be within this red area. And through modeling, we were able to determine that by treating just this smaller area, where 77% of the contaminant mass was, you can more cost-effectively treat that, and the overall flux of mass from the remaining source was low enough where the groundwater conditions would meet the regulatory criteria at the property line in the Sentinel well. So it was an effective way to improve the overall efficiency and get the best bang for the buck on that type of application. So kind of running low on time, so I'll just go real quickly through this last case study here. This is a site, Superfund site up in Maine. This goes back to some of what Dennis was talking about. We were looking at a catalyzed hydrogen peroxide application. The original test was done where the oxidant performed very well, peroxide, but when we looked at it, second look, said that it really only is stable and lasts for maybe a little over an hour in situ. So that is a problem. It looked great in the bench, but when you try to spin that into a full scale, you realize there's an issue there. So we went to a pilot scale, and we did, in this case, this is unusual, but we were able to do a side-by-side test using persulfate and another area using peroxide. So we had a peroxide test area and a persulfate test area. And this will, and here's a picture showing what that layout, pilot layout. So it was a fairly large injection that was done, even though it was a pilot scale. And so where did the oxidant go? So we did the application, and by looking at with our monitoring program, which was enough where we were looking at pH, conductivity, ORP, those sorts of things, we were able to see, if I can see it, we had quite a bit of distribution of the oxidant solution, and there was a major preferential pathway along this edge of the site. And but we covered the test areas pretty well with both oxidants. However, when you look at what was actually happening, these much smaller blobs of oxidant influence, this is showing where the oxidant was actually effective. So if you look at where the persulfate, the orange was, the oxidant was active and it was still reacting and it was covering most of our target area. The peroxide, these little purple areas are showing where the oxidant was active, and then outside of the purple is where the oxidant was fully reactive. So even though we were seeing the influence of the reactive solution going quite a large distance, it was only really going a foot or two outside of the injection well. And so those are the kinds of things that are important when you're looking at your oxidant stability and you're doing your pilot test. You can have all kinds of indications that show that your oxidant is going where you think it's going, but when you actually look at all the data, you can see that you need to be looking at some other parameters, such as the stability of the oxidant. How effective is it when it's getting to where it needs to go? And so there's a picture of, that's Dennis on the left and me on the right there. But overall, it's just solution distribution versus the effective distribution. Your monitoring can tell you what's effective and what isn't. And careful evaluation of that data. Oxidant stability is very critical to these designs, as well as just as important as the preferential pathways in this case. And yeah, I think that was the end of that. And I think I'll end it there because this other case study was just showing even in a rough site where the rats are stealing your lunch, you still have time to do it right. And this was a rush, a very high rush job where construction was ongoing, but we insisted that a bench test need to be done, and it was done. And even when you're in a rush, it's critical to do these tests and get the right design data to make sure it works. I know I kind of ran almost to the end here. So Dennis, if you want to wrap it up.
Yeah, sure. So thanks, Scott. I appreciate that. So again, our conclusions really here are the poor performance and failures out there are associated to skipping kind of a lot of the pre-design engineering type work, which includes the treatability testing and the pilot testing to understand kind of the overall conceptual design of the site and how the oxidants are going to react with the soils, the contaminants, and the other site features there. So, and some of the big negatives or the big consequences of that are A, no apparent effect, or as in the case study I presented earlier, conditions in the subsurface with TCE as far as that CHP, catalyzed hydrogen peroxide application actually got worse. And then obviously the issue is rebound, and then ultimately for the client, cost is a big issue. So those are kind of the big overview as far as what we want to get across today during the webinar. We've run out of time, so what I'm going to do is we're going to save the questions, and what we'll do is we will answer them directly after the fact, and we'll do that in the next several days that we can get those answered. And then, as I mentioned earlier, there'll be an email that goes out that gives you a copy of the presentation, then also a recording of the webinar at this point. So again, thank you for attending. We really very much appreciate it. Hope you were able to learn a little bit from it. I think Scott would agree with me that we barely scratched the surface as far as some of the more technical aspects of chemical oxidation applications. But if you'd like to talk to us about it, give us a call at any time. And again, thank you very much. Appreciate it.
Thank you.